good? So our next speaker is going to be taking the place of Amit Singer, who will be talking this afternoon. Is Ben Recht from the University of Wisconsin Computer Science Department. Ben got his PhD from MIT and has most recently done some very beautiful work, some of the initial work really on low-rank representation of matrices and recovery of matrices from very few data samples. So Ben, thanks.
Thanks, Larry. So this one actually might, or should I stand closer to this? I'll stand closer to this. I'd like to thank the organizers for giving me the opportunity to speak a little earlier, because now that will give me the opportunity to actually enjoy the rest of the program, which actually was stocked with amazing stuff. And I'd like to thank Ingrid for rushing here from the airport, because she is not someone I would ever hope to be able to give as beautiful a talk as. That said, I would like to talk about a problem that I think we're all interested in. I think it's going to be a kind of recurring theme throughout the day. It already appeared in Ingrid's talk and Pierre's talk, and we'll see a lot more examples of today. It's just really simple. We just want to find a solution of an undetermined system of equations. That kind of underlies most of high-dimensional data analysis, because we can't hope to actually store or acquire enough information to, about a lot of the signals that we are interested in. So in this case, phi is some matrix where the number of rows is considerably less than the number of columns. We just want to say, you know, there's probably an infinite number of solutions. Let me promise you that there's one. And the question is, with that promise, which one do I pick? So the key ideas that we've seen a lot of attention to, as Ingrid said, for 40 years, maybe would be leveraging the structure of sparsity. Maybe a little bit more recently, we could also leverage the structure of rank. For example, this hidden X could be a low-rank matrix that we're looking for. Another very popular and powerful prior that we might have on X is that it's smooth, that somehow the coordinates are linked to each other or correlated to each other in some spatial way. And finally, we might know that X is symmetric. In all of these cases, that allows us to actually summarize X with far fewer numbers than the ambient dimension, and perhaps with far fewer numbers than M, the number of observations. And the question becomes, if I know this, if I know that I have some latent structure that defines my hidden X, or that constrains my hidden X, how do I actually build an algorithm to find X, given these constraints? And secondly, how do we analyze algorithms to find X? So what I want to do is actually just go through the catalog of examples that people have already looked at, and then see if we can kind of draw some conclusion about what ties them all together. Okay? So the first example is sparsity. Now, there are lots of different ways that we can get to the notion of sparsity, but I'm going to follow one that was presented in some of the early work in compressed sensing, notably in a paper by Candace, Romberg, and Tao. So here we have the set of one sparse vectors. Each of them have norm 1. If I draw their convex hull, it turns out that that is the unit ball of a norm. And that norm is the L1 norm, okay, which is the sum of the absolute values. And this holds in any dimension I want. I can only draw 2D cartoons for you today. Now, why do we minimize the L1 norm? There are lots of different reasons, lots of different motivations, but my favorite picture is this. Let's just say I have some random subspace, some random affine space, phi x equals y. Now, what does it mean to minimize the L1 norm subject to those constraints? Well, one way of looking at it is what we're going to do is blow up that unit ball until it's just big enough that it touches that affine space. And then our optimal solution will be that first touching point. And you see, in my very suggestively drawn picture here, that the first point we touch at is one of the corners, is one of the sparse solutions. And maybe that is something generic. And indeed it is. And that kind of underlies the whole theory of compressed sensing, is that fairly generically, under a variety of different models for phi, we can actually expect that the sparsest solution will be the first touching point when we solve this problem. Let's go to another problem that's very dear to my heart, which is finding low-rank matrices from sparse samples. So in this case, here is I'm going to just make the exact same cartoon. This is the set of now 2x2 matrices plotted in 3D. Now I made them symmetric. We want only the rank 1 guys, because those are the models we think are simplest. And I'm going to restrict it to just be the guys who have norm 1. All the rank 1 matrices that have norm 1 under this parametrization of those 2 ranks. Now I could do the same exact construction. Let's just take the convex hull. And we get this soup can-like object. The soup can actually turns out to be the convex hull of a norm. It's a very generic kind of thing we're seeing here. And that norm actually is the nuclear norm, which is equal to the sum of the singular values of the hidden matrix. And if I just draw the same picture, I can't do the animation as well with this particular graph, but again, I'll just take a random subspace, phi x equals y, it's in red, and then I minimize the nuclear norm subject to that particular affine constraint. And what one can prove, and what I proved with Marian Faso and Pablo Perillo, is that generically, again, you touch at the lower rank solution. You touch at the lowest rank solution first. And hence that reduces the number of measurements you might expect to take. And that kind of gave rise to all this stuff about rank minimization and matrix completion as just basically kind of building on basically that picture. I'll do one more example. Actually, basically this talk is just going to be a lot of nice examples. So here's one more example, integer programming. Perhaps not really this is not really a sparse modeling problem, but here is the idea that I know I want one of the corners of some hypercube. I know that I have some measurements of some binary vector, and I want to know which one. The convex hull in this case is the L infinity norm. And again, you have the exact same picture. I blow up that L infinity cube, that hypercube, and I'm going to touch on one of these corners. And using that intuition, Donahoe and Tanner and Mangasarian and myself independently showed that, again, if as long as the number of rows in phi was sufficiently large, in this case, actually has to be very large, as you might imagine, specifying just the bit sequence itself requires about n over 2 numbers. We showed that you need n over 2 random measurements will also suffice. And again, the same intuition holds in this case. So the question is, so what's going on here? What underlies all these models? You kind of got the picture. It was, we had some model x, right? And x, we've said, could be decomposed in terms of some simple atoms. I don't know what these atoms are. They could be a dictionary. They could be some manifold, like was in the case of the rank 1 matrices. They could be some algebraic variety. I don't really care. We have some infinite set, perhaps, of atoms. And we want to find the smallest linear combination of those atoms that gives rise to this model. And to do that, okay, that seems like a hard problem, but what do we do? We minimized the sum of the absolute values of the coefficients of the weights subject to this decomposition holding. That was exactly the algorithm. Okay, so it looks like the L1 norm, but now note that we're also allowing ourselves to let the number of different decompositions, we're just ranging over the alphas and the w's simultaneously, which looks kind of weird. But that's always a norm. It's always a nice convex norm. So it turns out that this is not just restricted to, and people have kind of stumbled across this idea all over the place. So let me give you other examples which maybe haven't quite been tied in with compressed sensing, or maybe not as directly tied in with compressed sensing. One example is in unions of subspaces. I think this is actually one of the more concretely tied in with compressed sensing. In this case, what I tell you in advance is that the signal comes from a sum of unions of different subspaces. So in particular, this could be like tied in with the wavelet trees that Ingrid spoke about at the beginning. We could have maybe a dictionary of image patches that would have some particular structure, and we know that only particular leaves are going to be explored. We could also know that we have a signal that's been translated over time, and we're going to have a sum of those translates in a multipath problem. Now, what am I going to minimize here? Well, I know my atom should lie, oops, one sec. I know that my atom should lie in one of these subspaces. This is my subspace is UG. So if I just make that same construction, I'm going to take the convex hull, what do I get? I get this thing. Basically, you minimize the sum of the L2 norms of all the different WGs, where these guys live in one of the subspaces, subject to the decomposition holding. And this actually was proposed in an early group sparsity paper by Jacobo, Buzinski, and Ver. Okay. Here's another example, permutation matrices. Maybe I have some kind of ordering or ranked election that I would like to try to determine what's the appropriate ordering. Like the BCS or something, right? So we have, or maybe we're trying to track multiple targets. We're just trying to keep straight which one is which. In this case, X would be like a sum of different hypothesized permutation matrices. And the convex hull of the permutation matrices is a well-known polytope called the Birkhoff polytope. So we can minimize our data subject to agreement in lying inside this Birkhoff polytope. Now, if time permitted, I can give a lot more examples. So I'm just going to have my slide of other things I could come up with. So for example, there are problems involving moments that can be phrased in this way. And those problems can be solved with semi-definite programming, again, coming up with the convex hull. Cut matrices, which come up in genetic networks and come up in clustering problems. Those can be now not exactly solved with semi-definite programming, but the convex hull can be approximated with semi-definite programming. And then there are problems with tensors, where we'd like to actually take a data matrix or a data cube and decompose that into small rank 1 tensors. And those problems can be approximated with alternating least squares type algorithms. again, approximating the convex hull constructions that we're talking about. So we have kind of this like whole ubiquitous kind of thing of we take some simple models, we take their convex combinations, we get some penalty function out. And that penalty function tends to be this thing, which I call the atomic norm. This is just because I have a penchant for bad puns. We had the nuclear norm before, and now we have the atomic norm. And then I don't know what we're going to do after that. We kind of run out of nuclear physics to tap, I think. So here's the idea. It's actually just, it's kind of a standard thing in functional analysis. The atomic norm is just, it's called the gauge function. If we didn't want to be cutesy, we call it the gauge function. The gauge function is just the smallest t such that x touches the convex hull of A, blown up by that factor t. This has a long history in functional analysis and approximation theory. And when A is centrosymmetric and basically contains a nice unit ball around the origin, the convex hull contains a unit ball around the origin, this is a norm. And it actually has exactly the form I told you about before. It's the sum of the absolute values of the coefficients, subject to searching over all possible decompositions over the atomic set. So here's the idea. This is basically our prototype algorithm that we want to analyze for the rest of the talk. I want to minimize this atomic norm subject to my data, which is phi z equals y. The question is, when does this actually work? When does this give me this hidden x that I promised you actually was there? And the second is, how do I actually solve that optimization problem? And those are two questions we want to talk about for the rest of the day. Okay, so we just want to kind of go back to that picture that we had before and kind of fill it in with a little bit more rigor. Okay, so I'm going to define something called a tangent cone, which is a standard thing in convex analysis. I have this ball, which we can just assume to be the unit, the convex hull of A. I'm going to assume that x lies on the boundary of that convex hull. And the tangent cone is just all the directions that make the norm smaller, or all the directions that point inside that unit ball. Okay, it's a fairly straightforward notion. Now, let's assume that I'm minimizing this function, the atomic norm, subject to these equations holding true, phi z equals y. So I know that x satisfies those equations. Here, green is going to be the set of all feasible directions. And when is x the unique optimal solution? Well, basically, it says that if I can, the only directions I can move and stay feasible are those that lie in the null space of phi. And so it's just saying that the directions that lie in the null space intersected with the directions that lie in the tangent cone have to be only 0. It just says x is a unique minimizer if and only if the intersection of the cone with the null space equals 0. Okay, so that gives us kind of a simple thing that we can check now, right? We just want to say, when does a cone intersect some subspace at 0? So let's bring randomness into this game, because and you knew that was coming eventually, because we know that these problems are generally hard, and we're not going to be able to say something in complete generality. So let's assume that phi now is a random map, maybe a random Gaussian map, or a random Bernoulli map. In that case, maybe we can answer this question, because this becomes a little bit easier, because we could say, when does a cone that I'm going to fix intersect a random subspace at 0? When does a random subspace U intersect some convex cone C at the origin? Now, it turns out that this machinery has been developed in the functional analysis literature for us, and so we can just kind of try to apply it. And the main theorem that we use in our work is a result due to Gordon, which says the following. As long as the codimension of U exceeds something called the Gaussian width of the cone, I'll tell you what the Gaussian width is in a second, then the intersection is the origin with very high probability, exponentially high probability. Okay? And so what is the Gaussian width? Well, it's the expected value of the support function of the cone where we're evaluated at a Gaussian random variable. It's a very peculiar construction. It's due to Gordon. But actually, it turns out that we can exploit nice duality structures and actually compute these for almost all the cones that we care about. I'll talk about in a second. But again, the moral of the story, the corollary that we just take from Gordon's very powerful theorem is this. For an inverse problem, if phi is just some random Gaussian matrix with m rows, you just need the number of rows to exceed the width of that cone squared to guarantee that you get recovery. So that's the corollary we want to take away. So we have this weird Gaussian statistic, the max over all the points in the cone intersects the sphere with a Gaussian random variable, and we take the expected value. Let's just take it on faith that that's actually what we need to compute. But once we know that that's what we need to compute, that gives us bounds on the number of measurements we need to uniquely determine objects and with the atomic norm. So what's also really nice is, again, this follows again from Gordon's analysis. applying it to the specialized problem, most of the time we have like noisy problems. We have sparse approximation problems we'd like to solve. In this case, we can extend the theory straightforward again, and it turns out that the width, again, is the key ingredient that you need to determine things even robustly. So in this case, we're solving a cone constraint problem. We're saying, look, I know that I have some disturbance W. I'm going to minimize the atomic norm subject to lying inside of this cone. And then if I get an optimal solution to this optimization problem, and X is the point I care about, I can guarantee they're close. Again, as long as the number of measurements exceeds the width times some constant factor. And the idea here, again, is simple. All this width is really telling you is something volumetric. It is telling you how pointy is the cone at X. And so if I make a little tube, this is my delta ball around my affine space, if the cone is very pointy, there's no way that you can move too far inside that convex ball. Okay, so now the question is, how do we calculate these things? So we use some nice tricks of duality and symmetry that actually let us get very, very surprisingly tight bounds on a variety of models that we already know. So for example, just using a simple symmetric argument in the paper, we can show that the number of points you need to uniquely determine a vertex of a hypercube is n over 2 with random measurements. And you would expect that you can never go below that. Actually, you can prove that that is the optimal bound. That is a tight bound. So how about for sparsity? Again, we have like a Bernoulli random matrix or a Gaussian random matrix. In this case, the number we get is this. It's a little messy expression. But we kind of wanted to throw all the constants in. Again, I want to say that all these results are not asymptotic. These all hold with kind of exponentially high probability in the dimension. So to read this off, we have the sparsity S, and n is the vector, and we get 2 times S times log n over S, maybe minus 1. Now it turns out that that also is proven to be an optimal rate, and I think, to our surprise, this is the best known bound that's not asymptotic. That proves that the compressed sensing problem actually works with this number of measurements. Okay, how about block sparse, or these unions of subspaces? Either we have something that's a block sparse vector, or maybe we have one of those overlapping wavelet tree examples I had at the beginning. We're going to have m total groups. The maximum size of any of those groups is going to be b. I'm going to say that our particular signal has only k of them active. The number we need in this case, again, is 2 times k times log m minus k plus b. Okay, it's a little bit messy. But again, very small constant, and again, pretty much optimal scaling with respect to all the parameters. And finally, my favorite problem, the low-rank matrix recovery problem. In this case, we have an n1 by n2 matrix. I'm just going to assume that n1 is less than n2 or something. The rank of this matrix will be R. And again, you go and you construct the width, and you see that the number of measurements you need is 3 times R times n1 plus n2 minus R. Okay, what is this number? Well, if you take the 3 away, that's the number that you need to specify the SVD. So you can never do less than that. And so we're off by 3. Again, using this. Okay. One more theorem, just for full generality, what can we say? So let's just suppose we have some cone. And I didn't talk about polar cones today, but for folks who know, polar cones are basically all the guys whose dot products with a particular cone are negative. And let's suppose that the polar cone has some measure mu on the sphere. Okay, we're just going to say that's the width. How many of these guys could we pack into a sphere? Basically, 1 over mu. So it turns out that the width of the cone is then completely controlled by the log of 1 divided by mu, up to some constants. Another way to think about that, let's imagine I have some polytope, like the permutahedron that we talked about earlier, and I want to specify one of the vertices. Okay, so that polytope is completely symmetric, so all the cones have to have the same volume, and so the total sum of all these cones has to be it has to be 1 over the number of vertices. We apply our theorem, and you find that log number of vertices measurements are sufficient to recover the vertex of a symmetric polytope. So again, using symmetry, we're able to dramatically reduce the amount of measurements you need to determine symmetric objects. So for permutation matrices, this calculation tells you that you need about n log n measurements to actually determine an ordering. And for cut matrix, you need about O of n. And the cut matrices are the things that come up to determine clustering in a variety of scenarios. Okay. All right, so we answered the first question. How many measurements do you need? When does this work? We kind of have a fairly decent understanding. It gives you very sharp, precise numbers about a variety of different priors. Now the second question is, how do you actually solve it? And it turns out that actually can be somewhat universalized as well. Typically, we like to solve these lasso-like looking problems. Here we again have phi times z minus y. This has kind of been our standard thing. We have our L2 norm on this object. We want to minimize that L2 norm plus this atomic norm penalty. This has kind of been a very popular thing. If you turn that A into a 1, you will find 400 papers about good ways to solve this problem. and then most of the, it's awesome, like half the inventors are in the room. It's good. So now what's the algorithm that everybody uses? The very popular algorithm for L1 is the same one that we're going to talk about, and it's basically this kind of iteration between stepping along a residual vector and doing some kind of projection or shrinkage. Okay, so the shrinkage operator, this pi out here, is just you can always write it as the argument of this simple L2 cost plus tau times the atomic norm that we've been talking about. And this residual here, Rk, I failed to define in this slide, it's just your error. It's just phi z minus y. That's all Rk is. So it's basically the algorithm is always, how wrong am I? Project back, and then project it down with a shrinkage operator. So in the case of L1, this is a very simple algorithm. But for other cases, when we have a generic atomic norm, maybe this isn't so easy. But it turns out that as long as if I can approximate the atomic set, then actually I can solve this problem. And there's basically a whole theory of relaxations that basically says that if I could take a set and then maybe come up with an outer approximation, well, then I could solve the problem on the outer approximation, and maybe I can get decent bounds in that case as well. And so there's a whole hierarchy of these things in our latest paper based on something called theta bodies. This is this interesting thing from algebraic geometry. They give you tighter and tighter semi-definite relaxations, but whichever one you want, you always know that the quality of the approximation by A2 is basically going to determine how well your approximate shrinkage algorithm is going to give you sparse solutions. And the thing to note here is that whenever I make an outer approximation, these cones are getting wider. So just beware. You don't want to do, not any approximation is equally good. Okay, so to wrap up, we kind of proposed a very straightforward thing. We used our intuition and followed basically what we'd already seen to propose a natural convex heuristic, and we kind of showed that it has some really, really nice properties. You get very nice tight bounds on a variety of problems we already knew. We're able to actually solve problems that we didn't know how to solve, or at least come up with bounds on measurements of things that we didn't know before. We get stable recovery without having to use restricted isometry or Grassmann angles or any of that stuff. It just comes for free. And there is kind of like a standard way to compute these bounds and solve algorithms. Now, there's a lot more to do. And actually, I have like 4 minutes? Good. Okay, so there are lots of extensions. I'm going to tell you about one. So basically, one thing that would be great to do is actually compute more widths. Because I think we can come up with a lot more priors, and these things are fairly straightforward to calculate. I think that will give us a lot more insight about what structures are actually easy to recover or not. It would be interesting to actually kind of incorporate better noise models than the ones we've been looking at to actually kind of look at statistical problems. I want to understand basically the loss that we induce with our semi-definite relaxations. But I think the thing that's been keeping me up at night the most has been how do we actually make these things work on real data? How do we actually scale these things? How do we actually implement these things on real data? So I've been fortunate to have spent the last 2 years in the computer science department and learn a little bit more about computer science. And in particular, I'd just like to finish, I got about 2 minutes, just with a quick overview of some very recent work that I've done with my colleague Christopher Ray, who is a data management expert. He's also a coding whiz, so he really can make things run much faster than I'd ever. He taught me all about the 04 flag. That's a very interesting flag in GCC. You have no idea what that thing's going to do. Anyway, so let me give you a particular example of how we might actually use the structure of the atomic norm itself to actually push the algorithms to really, really fast speeds. And in particular, how we can use them on multi-core to do parallel implementations. So this is an algorithm called Jellyfish, and I'm going to give you a specific example. It's for a variety of different matrix factorization problems. Let's talk about the nuclear norm. The basic idea is just let's approximate this nuclear norm by first approximating the decision variable by product, L times R, where L and R are very tall, so they have very few number of columns. In this case, one can show that you can have an equivalent formulation just in terms of the L2 norms of L and R plus this kind of penalty term. And an algorithm for solving this, which actually I think Robert Bell will probably tell us about on Wednesday, is the following. Just pick a random U and V, compute the residual on that random U and V, and then shrink that. Oops, how'd that happen? And then shrink that. This is exactly that iterative shrinkage thresholding where we do one example at a time. This is sometimes called stochastic gradient. So we pick a random U and V, we compute its residual, and we shrink L and R correspondingly. Now, I'm almost done here. So basically, the whole idea of what we did is you use the fact that the atomic norm tells you that we should be able to have a decoupling amongst blocks if we have certain measurement patterns. So in particular, if I did not observe anything in these white blocks, but only on these big gray blocks, I could run the 3 gray blocks independently of each other, and they would never talk. And so our approximation algorithm is to actually just do that, pretend like we're only observing things in the gray blocks, and then we'll shuffle the data and then run on these off-diagonal blocks. Here we go. L1, we'll run these blocks in parallel, these blocks in parallel, and these blocks in parallel. And the big win here is you don't need to synchronize, and you don't need any mutexes, and you don't need to write particularly interesting threads. You just run them in parallel, and they don't have to talk to each other. So it kind of looks like this. Here's I'll close with this kind of funny animation. Here is our matrix laid out the way it's given to us. We shuffle all the rows and columns just so we get a random instance. We apply a block partitioning, and we solve on that block. Then we would solve on the off-diagonal blocks and this last off-diagonal block. Then we shuffle again, and we continue. Again, we're doing these in parallel. And we recently were able to buy these 40-core machines and just run it in parallel. And you get to, what's amazing about this is that there's no loss in the actual approximation. You get the exact same bounds that you were getting before. But now we can solve it, like, for example, the Netflix prize, which has 100 million examples. It's a very, very large problem. We can solve it in under a minute on this machine, just doing this parallelization. So the question is, what else can we do? It's kind of lets us ask the question, what else can we do, taking with all the advent of all this new multi-core technology, machines that have 40 cores that you can buy for $15,000. What else can we bring to the table that actually allows us to scale the algorithms we're working on to really massive data sets, to be able to run them in very short manners of time? And with that, I'd like to thank you for your attention. I'll take any questions you might have.
We're right up against the break, but we'll take a quick fast question if anybody has one. All right, people want break. All right,
Yeah, so.
That was spectacular, man. That was awesome.